It's a pleasure that you are here to this first educational lecture conference in the PRELUDE project. The title of this first Communication Inside Educational Event series is Proactive Forecasting and Optimization Approaches for Intelligent Buildings. It's organized in an hybrid mode. So someone is in presence here in Turin, other people are connected remotely, and this is also the approach that we will follow for future events in this educational series. Broadly speaking, this educational series is part of task 9.5 on educational works inside the project Preludes, that is working for proactive integration and improvement of intelligent technologies in buildings. Today we start a series of lecture that will be multi-topic lecture like today, more lecture conferences or more focused communication one to expert in a longer time on specific topic. It will be held in between this year and the next one, and will work in this hybrid, partially in presence and partially in remote participation. The topics as the one of today, so proactive forecasting optimizations and approaches for intelligence building. We will follow with other communication, one in March, one expected in May and July, about maximization and exploitation of free-running passive hybrid building potential, one about climate change and comfort and bioclimatic architecture in next and new innovation aspect. And after, from October, January, on the end of this year, beginning of the next one, we come back on more ICT and ET issues and topics, supported UT, BMS, and so on in the built environment. The people and the speaker invited are recognized experts, both for scholars in architecture, both for industries or for potentially professional, including clearly PRELUDE partner, as today the presenter will be everyone from the PRELUDE partner domain. It's addressed to students, this type of events, university students, clear to professional, but also to interested people and people working in general inside the built environment and digital innovation for the built environment. Events will be recorded and the record will be shared inside the PRELUDE portal, thanks to the support of Unismart, which is leading the project communication and dissemination. On this point of view, the event of today is the first of the series of lecture. We will present different approaches and aspects correlated to buildings management and optimizations, including machine learning approaches to buildings and forecasting algorithms in general. Speakers in this case come from academic and industrial world, and you will see how these aspects are treated inside the PRELUDE project in partial and in other aspects in general. If you see, and speakers are from the red-colored countries inside the PRELUDE domain. The program of today, if we skip the presentation that I'm doing now, starts with Professor Michael Pomianowski from the Aalborg University in Denmark, that he will introduce as project coordinator the PRELUDE aims and challenges, supporting the fact that the Prescient building operation utilizing real-time data for energy and dynamic optimization, how these are treated inside the consortium, which are the objectives, I think, of the project in itself, and how PRELUDE platform is supported to integrate different models and so on. So we will make the general introduction to this project and to all of the aspects that we will treat during the year in which we are involved on it. After Pomianowski, it will be the presentation of case day from TREELOGIC company, which is set in Spain, that will present the working that they are doing on scaling up technologies for multiple model aggregations. In this case, in the context of the PRELUDE projects, we will support how they work for efficiently aggregate models in multiple building scenarios, how to pass in between the scales from single building to the district, how generate knowledge and intelligence at scale bonds and aggregation of the individual ones, and how they use elements, forecasting and clustering aspects to support consumption profile clustering and forecasting for the next 24 hours. After the 3 presentations, the next one will be done by Nikos Sofias from CORE in Greece. That will be about machine learning solution for weather and energy forecasting and energy efficient building. Again, inside the PRELUDE scope project, CORE SC will propose and will show the data-driven methodology that they are following, based on machine learning, mainly for supporting local climate, weather, and energy forecasting at building level and support. We will see how they will use and how the forecast successfully support to arrive to predict energy consumption in buildings. That clearly is crucial to support energy management, planning, and functionality and optimization at residential building level. And also, we will see this approach is applied and will be applied in PRELUDE on real demo cases on, again, a 24-hour head interval. At about 10:20, 10:25, we will have the presentation by Christian Helsch from FB Furchtburgenland, a research and innovation center in Austria, said in Pinkafeld, and in this case the presentation is titled The Energy Saving Potential of Data-Driven Predicting Control. Again, in this case we will see the needs for decarbonizing and reducing the energy needs by our buildings toward an energy efficiency of the building sector is supported in their work to support intelligent building energy management systems using model predicting control strategies and approaches. In this we will see how traditional MPC can be implemented with more advanced data and more innovative data in a data-driven predicting control approach. That is the one that they are applying to their living lab. I think after that, we will need a small break, I think, eventually to take coffee and things like that, and we will come back at 11 with other 2 presentations and a larger question and answer session. The first of these last 2 presentations will be led by POLITO. It will support the use of a new white box modeling platform using Energy Plus to support energy simulation of building behaviors. In this case, the scope is to predict the next 24-hour thermal comfort in free-running building to optimize and to predict the optimal scheduling on shading and ventilation based on weather forecast. After that, there will be the presentation by STAM, an Italian company supported by Mattia Repossi, and in this case they will present the EnPower platform, which is a platform prepared by the company in itself, the support user in controlling and optimizing the HVAC system in houses to support and arrive to guarantee thermal comfort and indoor air quality in real time, synchronizing home devices and platform elaborations. The essential thing also in this case is to support, for example, low distribution of electricity or other aspect to arrive to forecast the optimal schedule of operation in order to reduce the energy need, and also in order, much as possible, to reduce network problems by the sense to have smoothing the power peak of the electricity demand and in general energy demand, which are the more costly one, and also that has the more difficult to be managed by the grid. I only remind that this type of work in the educational event series is part of a larger educational activities series and events that also include the development by students, telecommunication students, of monitoring kit, do-it-yourself technology, more advanced, clearly to support citizen science monitoring students to students. So the university student develops the kit that will be used for monitor high school schools to support and spread ICT topic and IoT topics in education, to reduce and increase the thermal comfort and reduce energy needs. So I thank you very much, and I leave the floor to Professor Pomianowski.
Good morning, everyone. Good morning, Giacomo, and thank you for organizing this event and for inviting us to give the speeches for the POLITO students. My name is Michał Pomianowski. I come from Aalborg University from Denmark, and I have a pleasure to coordinate this project, which is a 42-month project. It is a Horizon 22 innovation project. Currently, we are in the 26th month of operation of the project, so we have still several months to go to finish our work, but we should be quite advanced already now. With this presentation, I will give you the overview of the project, so that I will prepare in a way a ground for the next 5 exciting presentations from the technology providers that are part of the consortium, that today will focus on being proactive, on machine learning, about forecasting. So what is PRELUDE Consortium? We are 21 partners from 10 countries, and we cover from north to south almost entire European Union. We have industrial partners, several. Some of them come from Italy, such as Iron, LASIA, STAM. We have demonstration providers. These are different partners that often have also another function in the project, but we have 5 demonstration cases, such as real buildings, and we have 1 living lab building where we validate and do the initial testing of the technologies, that is located in Austria, in Forschung-Burgenland. Then we have also several research organizations, such as Brunel University, POLITO, Aalborg University, Forschung-Burgenland, Tampere University, Unismart, that have a more scientific approach to the developments that we carry out within the project. Now, why projects such as PRELUDE? What are our focus areas? Well, to be short, I have listed these focus areas, which I think have a quite dominant part in the project. The first one is about realizing energy efficiency. Although we think we build energy efficient buildings, they are in operation very often not energy efficient at all. The first place where you can actually determine if building is energy efficient is when you collect the data and start to analyze the data from these buildings and to assess what is the actual operation of the building. Here we look into the energy efficiency, but of course we have to also look at the comfort condition, because these two are strongly dependent on each other. The second focus area is about data-driven building assessment, which is of course linked to the first one. So many things and activities that we do in this project is data-driven, which means we are dependent on the data availability from the buildings. This is both energy measurements and indoor environmental sensors in the building. The third focus area is about data transferability and accessibility. These data, or these sensors, this hardware, send the data from the buildings, and we work around how to make this data available in a best way for the different technology providers, and how to make this data accessible and transferable also between the partners, so the technology providers. In the project, while it was actually carried out, we discovered that we have different building smartness levels in our pilot cases. So in the project, we can say that we cover different automation and smartness levels of the building, from low tech to middle tech to, I would say, high tech buildings, where the living lab case, which is the most advanced building, is the high tech building, high automation capabilities. And the last focus area is to have adaptable solution, which means it is adaptable for each building. We propose a modular concept, which I will show you in the next slide, where actually the building can be served with different functionalities of our platform that are provided by different technology providers. Here in this slide, you can see the concept of the project, a PRELUDE project, which is developed a platform that can integrate three areas. The first area is about data acquisition and aggregation. This data acquisition is collected from single buildings. It can come also from the district level, such as, for example, district heating system with smart heat meters, or from community level, where the focus is on electricity sharing and electricity production sharing. So the first layer is the data acquisition. This also includes the weather condition. The second area is our middleware solution, which you can see in the middle of the slide, which integrates the data from the buildings, and it integrates also the accessibility for different technology providers, which is the third area of the project and the platform, which is the functionality agents or technological agents. We have several of these agents developed in parallel. Some of them focus on comfort condition in the building and improvement of this. Another focus on energy conservation measures and optimization of energy. Some others focus on predictive maintenance of buildings, or on renewable energy systems or renovation of buildings. Today, the focus area is on proactiveness, forecasting, and optimization. And as Giacomo has said, we will hear 5 exciting presentations. One of them will come from POLITO, which will be about the white box models, free running concept for the building, and 24-hour forecasting of comfort condition in the building that is supported by these models. The other presentation that you will hear will be given by the TREE technology, which is about aggregation of the data and upscaling of the models. The third presentation will be given, maybe not in that order, but will be given by STAM, which is about their platform and concept for energy efficiency improvement in buildings, big savings, and also one from Forschung Burgerland, which will focus on data predictive control of buildings. And then one more presentation will be given by CORE, which is working on prediction of weather conditions and also energy balance condition in the building. I think I have captured all of the presentation that will be given here. Now, few words about the physics and our middleware solution. Well, this concept, or this middleware solution, is, in other words, decision support systems, which means it should support our work and make it more efficient. There are different functionalities of the physics. One of the first one that I would like to highlight to you is, well, if you have building as presented on the right side of the slide, and then you have several technology providers, if you would like to connect each of the technology provider to the data or with the data from the building, you need to make a connection directly to the building for every technology. This is not very efficient, and this is not very, maybe, this is not the favorite situation for the building owner or the tenant, where you have several technology providers every time separately contacting the building. Therefore, in our project, we have replaced this configuration with a central solution for the middleware, which is called physics, which can serve a data transfer between the building and different technology providers, and is bridging the data from one to another. It can also bridge the data from one technology provider to another, so the data is more easily accessible by each partner in the project. On top of that, physics not only acts as a middleware, it can also aggregate data from various technological level buildings. It can integrate simulation and forecasting technologies. So this means it can integrate all of these technology providers that provide this kind of solution. Generally, it can enhance intelligence. In some cases, it can schedule and run simulations. And it can as well provide the feedback in form of some kind of dashboards and proactive graphical interfaces to the end users. It can also control the signals to the building if the building allows that communication. Now, in this slides, I have highlighted some of the PRELUDE objectives. The first one is to provide information to the tenants or the building owner about the operation of their building, so that they can make informed decision about how their building is operating, how it could be improved, etc. The second objective is about securing and ensuring the efficient and comfortable operation of the building, which is related to the energy conservation measures, better controlling the HVAC systems, being proactive in this area. The third objective is to detect anomalies in operation of the building and provide predictive maintenance. This area is focused on active elements as HVAC components and also on passive elements. Here, however, I'm not sure about actually the development of this will be possible in the project. The fourth objective is about replicability and adaptability. So our concepts should be flexible and adaptable to different residential buildings, and should be scalable. And the fifth objective is about integration of the smart meter data and utilization of these data, so that the building can become a more active part in the grid context. And here we work both with heat meters for district heating connected buildings, and also with electricity for the electricity communities. The last three objective here is about renovation actions. Here we have also an action and objective to provide a renovation tool and scenarios with together with the accurate data about the financial consequences and costs related to this renovation. This is very important, so that the building owner can get a credible and reliable information both on energy savings, but as well on the costs of renovation. The seventh objective is about data security and GDPR. This is an answer to the European Commission requirements for the GDPR, which is very important from the regulatory perspective, so we have to obey that. I have to share with you that it's not easy, and it's very often giving us a lot of headache to actually fulfill GDPR compliance, to be compliant with that, since it always requires an informed consent being signed by the tenants, occupants in the building, that we collect the information from the building where they are. And the last objective is to validate the technologies that we develop, and also to demonstrate them in the real operation. And this leads us to one of the last slides here, where you can see that we have several pilot buildings where the technologies that I have mentioned in the concept slide shall be demonstrated, implemented, and on the right side hand, you can see a living lab technological building where these technologies should be validated, where we have a more control environment condition and more rich data information. Now, some of the conclusions so far. We can see that because of the residential buildings, we mostly work with the residential buildings. In residential buildings, IoT systems are quite dispersed. They are different commercial providers. Then our middleware has to communicate with these different solutions and protocols. And the first establishment is quite challenging, and we can see that we had to establish several different solutions for different buildings with different monitoring commercial solution. Once this is done, it is probably more easy to scale this up, but still there is there are some issues with data transferability, continuity of these, etc. So this is not an easy part. Another thing that we observe is that from the middleware point of view, there should be some kind of a standard requirements imposed to address this challenge of very different communication protocols, etc., because it is very time consuming. And if there do not come any regulations and standardization in this area, it might be very, very difficult and maybe not feasible to connect buildings to the service such as PRELUDE, because it is very time consuming and also resource consuming. On the other hand, we can see that middleware can provide technology enablers with the data from the building once this connection is established, and it can take all of this burden from the technology providers. So this is promising. Yes. The next conclusion that we have observed is that buildings require flexible assessment solution, both considering inputs and outputs, which means we different buildings will require different technologies, and our modular concept and approach actually fits in very well to this, because then maybe one building should more focus on comfort improvement, another building on energy efficiency, another one on renovation actions, etc. So in different periods of the building, they might need different services, and this is provided by PRELUDE. And the last conclusion is that our technology enablers, so the technologies, they are heavily dependent on the data from the building, and actually the level of and the density of the data very often determines, and also the history of the data very often determines to what extent we can develop and implement the technology into the specific building. Yes, with that, I would like to finish my presentation and give the floor to the Kais from Tree Technology to share his slides. I will now stop sharing my screen. So
So first, I would like to thank Giacomo for organizing this event, and thank you all for attending this lecture, but also for inviting us to give this lecture. Thank you one more time, Giacomo. Today we'll be talking about scaling up technologies for models aggregation. My name is Kais Dai. I'm data scientist at TREELOGIC. And before starting the presentation, I would like to introduce Tree Technology, the company I'm working in. Tree Technology is a research and development performing company providing information and communication technology solutions based on big data and artificial intelligence. We are work on different lines of business and on several areas of applications, as you can see in this slide. We have a strong R&D department. We are taking part in all of these projects that are mainly Horizon 2020 and Horizon Europe projects. Also these projects. And Tree Technology has a commercial brand. It's TREELOGIC, and it helps organizations in key sectors to improve their information systems, as I said before, using big data and artificial intelligence technology. And we do also have projects with all of these clients. Well, let's move now to the main objective of this lecture, which is scaling up technologies for models aggregation. The idea here is to improve the performance of energy predictive models by developing aggregation techniques in multiple building scenarios. And by multiple buildings, we mean the scale of neighborhood, district, and city. In other words, we are trying to generate knowledge and intelligence at scale based on the individual buildings data. That means that we are taking the predictive models to the scale of neighborhood, district, and city. But to do so, we'll need a data set in order to perform our analysis and to train our models, predictive models. So the starting point here is to find a data set with multiple buildings in the same area. And this is exactly what we did. We have obtained district heating energy consumption data set from the city of Aalborg in Denmark. The dataset has 3,125 building data along 3 years from 2080 until 2020 on a hourly basis resolution. And the variables of this dataset are mainly the timestamps, the heating energy consumption per building, the water flow volume, the inlet flow and backflow energy, but we also do have anonymized data with building typology, the number of rooms in each building, and also the building size. So we with this data set, we try to perform an exploratory data analysis. The first thing that we did is to analyze the correlation between the different variables, and we can clearly see here the high correlation between the energy consumption, the heating energy consumption with the volume flow, but also the inflow, in-water flow times the temperature. In the same line, we are trying to make a correlation analysis of the current, let's say the current observation with their respective K lagged values since it's a time series, in the first figure we can see that there is a high peak in the last 24 hours, so a higher correlation in data with the last 24-hour data. In the second figure, we are observing the same thing. So 24-hour data is important. There is a high correlation with 24-hour data, and slightly we have another peak at the 7th day, 168 hours. In this picture, we also observe the correlation between the different variables. This is what we have showed in the previous slide. Now, as we are dealing with time series, it's important to perform autocorrelation and partial autocorrelation. For the autocorrelation, it's a correlation between the current observation and the K previous observations respectively. And as you can see in the first figure, we have a cyclic behavior. So we are talking about seasonality. We have a seasonal time series. This is important for in order to build predictive models. And the partial autocorrelation, the second figure, we can see also a peak in the 24th hour. So this data is important also to we will need to take it into consideration for when selecting our variables to build the predictive models. Here to add some a note about the partial autocorrelation is that the correlation between the current observation and the K past observations, but by removing the contribution of the intermediate observations. In my opinion, it's also important to highlight the technologies that we are using here to perform either the exploratory data analysis or to model train and test our forecasting models. We are mainly relying on Python as a programming language, and we are not limited only to these three important libraries that we are using: sklearn, XGBoost, and HyperOpt. We are also using AWS, Amazon Web Services, such as S3 for storage and SageMaker for the notebooks, and Elastic Computing or EC2 service in order to instantiate and make the forecasting. As it's in an ongoing work, we are potentially will be using Spark and Elastic MapReduce to have a faster response from the models. And now, before diving deep in the aggregation methods details, let's set our baseline model. So for the baseline model, we choose a monolithic model for district level forecasting. We'll be using the Aalborg dataset that we presented before, and the idea here is to make a model to forecast to have the output will be a 24 hours ahead forecast of the district heating energy consumption, and will be used as the input the variables that we have mentioned before. Of course, after performing a feature selection process. Okay, it's regarding the monolithic model, the baseline. We used XGBoost as a regression or forecasting algorithm, Heschi boost stands for extreme gradient boosting. It's a leading machine learning or supervised machine learning technique. It's used mainly for classification, regression, but also ranking problems. What I would like to add here is we need to be careful with metrics we are using while training or validating or even testing our models. For example, if you are dealing with time series, I think it's not always appropriate to use, for example, the mean absolute percentage error, since we cannot divide by zero. We'll obtain infinite values and will not have a clear idea about how the model performs. We can use, for example, the mean absolute error, and there is also another metric that we can use, such as the mean arctangent absolute percentage error. This is an extension of the map metric, but using the arctangent, and it handles division by zero, but it's not symmetric, so it's less intuitive and interpretable. So maybe we need to use more than one metric to have a clear idea and compare the different models that we are building. Now coming to the aggregation techniques, we thought about two solutions. The first one is clustering-based aggregation. The idea here is to focus on the loading profiles or the curve shapes of the different buildings. The curve shapes of the energy consumption of each building. And the second aggregation method is the federated learning aggregation. We'll see later in this presentation, we'll give more details about each of these two aggregation techniques. Starting with the clustering-based aggregation modeling option, the idea is to start from left to right to scale up and start with the building level data. We have all buildings data on the left, so we'll perform the clustering. After that, we'll build a model per cluster. This model will give the cluster output, and then will aggregate the overall outputs of these cluster-based forecasting models in order to get the final output. The final output is an aggregated forecast of energy consumption. Well, for clustering, we are using the well-known K-means technique. So K-means is an algorithm, a clustering algorithm. And the idea is to, K-means aims to partition set of points into K clusters. Each point belongs to the cluster with the nearest mean, and it iteratively reassigns the points to the cluster with the nearest mean until cluster means no longer change. So we have a convergence as far as we move in the iterations. As you can see in the second figure here, the K-means iteration at 6 iteration, we start the K-means converge, and we can have this obtain the clustering result. The issue with k-means is to set the number of clusters. There are some statistical options that we can use in order to set the number of clusters, such as the elbow method, the silhouette method, and so on. So we do not choose the number of clusters randomly. There is a prior fine-tuning process that need to be performed before selecting the number of clusters. And coming to the clustering results of the Arbok dataset, we focus on the single-family houses. For only 2018, we have 2,459 building, and we choose to proceed by season. For example, for spring, we have 4 clusters. In the figures, you will see the hourly mean per season of all the buildings per cluster, and in the black line over here, I don't know if you see the cursor. The black lines represent the centroid of each cluster, and the fifth figure shows the centroid, the cluster centroids. So we clearly observe a difference between these centroids, and these are the clusters results. Also for summer, we have 5 clusters, autumn 4 clusters, and we only have 3 clusters in winter. In all of these seasons, we have a clear difference between the cluster centroids. Okay. Yeah. After performing the clustering, as I said, we need to build a model for each cluster and then sum up or aggregate the overall outputs of the cluster's models. And by doing so, we obtain our clustering-based aggregation modeling option. Now let's move to the second aggregation method, which is federated learning. As you can see below, we have the different buildings, and each building has its own local data. And we want to use federated learning, which is a new technology introduced designed by Google, that enables your phone to learn from rest of the devices while keeping your data private. So in the context of Prelude, the idea is to set a central model or a server-side model. We initialize this model and spread it to the different nodes. So after spreading the initial model to the different nodes, each node will start to learn or train the local model with the local data. After a certain number of iterations, and when the nodes will be available to communicate with the central node or the server side, they will send back the model update and not the data. We are not sharing the data. We are sharing the models updates to the central of the server. So here after doing so, in the central node will start to perform an aggregation process and send back the new or spread back the new model to the different nodes, and this this iteration will be done as long as the nodes will be available to communicate with the server. This leads us to have some advantages. The first one is the privacy of the privacy. So the buildings will no longer need to share their data to train a model. They only send the updates. There is no data leakage, and this is compliant with the GDPR, which is an issue in this case. So we are addressing this issue, and also it's highly scalable. So the federated learning applied in this context allow us to move from, for example, 2 buildings to thousands of buildings without any problem. And as a requirement, we'll need, in addition to the features that we are presented before, we'll need also the location, not the location, the specific location of the building, but the city location. This is to differentiate between a building in Denmark and another one in Spain or in Italy. And we'll need also a weather data in order to feed the models with these features. So I think that I've tried to describe our work in the PRELUDE project, and I hope you find it interesting. If you have any questions.
Thank you. Thank you very much, Kai. And after that, it will be Nikos Sofias from Core that will present the next series of presentation and works on machine learning.
Hello, everyone.
Hello.
Okay, this is Nikos from Core Innovation. I'm a data scientist, and in the PRELUDE project, we occupy with machine learning solutions for weather and energy forecasting in the energy efficient buildings. So in our presentations, we will dive in some machine learning basics, because I don't know the background of the audience here. Also some machine learning applications, also the application machine learning in time series, and in more detail in the energy sector. Then a few slides about the time series forecasting. Then in the context of the PRELUDE project, we'll see some explanatory data analysis in the time series of weather and energy time series for a demo site in the PRELUDE project. And then we will present some results about the forecasting of weather for a specific demo site, and the forecasting of energy consumption and PV power generation. So to start with, for those who don't know, machine learning is a branch of artificial intelligence who focuses on the use of data. This is a data-driven approach, and the algorithms of the machine learning try to imitate the way that humans learn, and so it can gradually improve its accuracy. Also, machine learning is a part of data science, as you can see in these 3 circles, where you have someone who is a data scientist has to know mathematics, computer science, and some domain expertise, for example, in the PRELUDE project, the energy sector. And in this context, in data science, the algorithms of machine learning are trying to make some classifications and predictions using some data. And the goal is to uncover some key insights, and in order to make some decisions based on the applications. Also, there is need for use of a large amount of data to train these algorithms in order to answer these business questions. So in general, machine learning algorithms can learn the hidden patterns from the data and predict an output to improve the performance of its own, based on the experience of its own. So for example, the simple linear regression model is of course a machine learning model where you have some data points and you want to predict the line, which is the machine learning model. So the categories of machine learning are these following: the supervised learning, semi-supervised, and reinforcement learning. So in the context of PRELUDE project, we are occupied with supervised learning because we have the inputs, which are the time series, and the outputs, which is the forecast of some values of the time series. So about the pipeline of the machine learning is here in this flow, in this arrow, where the two main parts are the data preparation and the machine learning part, where firstly you have to acquire some data, make some data analysis on those data and pre-process them in order to prepare them for the machine learning part, which is the model training, the optimization of the model's parameters, and then the evaluation on a new test set. And then you can have the model in production, as Mikhail said earlier, in the physics middleware. So some machine learning algorithms are presented here, which are, for example, the supervised learning, the regression that we're most focusing our project are some linear regression, neural networks, support vector machines, and decision trees. Also, there are too many in this branch. So the machine learning part here, what we have here is that based on some input, we want to produce an estimate about a pattern. Then during the training of the machine learning algorithm, the weights of the model are adjusted to reduce the discrepancy between the known examples that we already have and the model estimate. And this procedure is repeated as an evaluate and optimize process to update its weights and to have an optimal solution. So for the prediction part and the evaluation part, you have an error function which evaluates the prediction of the machine learning model. So in order to make a comparison between the predictions and the new data that you have, so to have an accuracy of the model. So some applications of the machine learning in real world, for example, in the manufacturing sector, you can have the demand forecasting or the process optimization. In the retail, some recommendation engines like Facebook or YouTube. Also in healthcare and life sciences, you can have alerts and diagnostics, etc. Also in energy, you can have some power usage analytics or smart grid management, etc. In our part, in the energy sector, the use of artificial intelligence is very crucial, and it also is a very modern approach, where you can have, for example, failure prediction or electric grid management, and of course the forecasting part. So about the time series. A time series is a sequence of observations collected from a process, most of the times, which is equally spaced periods of time. Some examples are the stocks, for example, the daily close price, or also some weather variables like temperature and energy consumption of a building. So the applications here can be the forecasting, the analysis, the process and quality control, and the anomaly detection. About time series forecasting, we use historical data to predict the future for a period of time. for example, 1 day ahead, 1 hour ahead, or a few months ahead in the future. The traditional methods include the moving average model, the explanation smoothing, the ARMA for those who are familiar with these methods. And about the machine learning models, there are a plethora. For example, the gradient boosted trees, support vector machines, and many types of neural networks like LSTMs and convolutional neural networks. So in this picture, you can see a time series and the forecast of a time series, where the challenge here, of course, is that the longer the horizon, the more difficult is to make accurate predictions. So this is the main difficulty also in the PRELUDE project for forecasting a time series in the future. So the machine learning smart buildings, the pipeline, I've already said before, can be depicted here, where you can have the dataset of a building, make some feature extraction, and then split the data for the modeling process in a training dataset and a test dataset. Then training the optimization and optimize the model. And after this process, you can have some predictions based on new data that you can have. So you can make a prediction of, for example, an energy variable. So what you can have here is a training set, the historical data, and the predictions in the future. Also, you can have here example for PV power generation, where you can see here in this graph the training set and the forecast in the future based on some input data, including the weather and the power data. Okay, so in more detail about the PRELUDE project, we acquired some data from the Living Lab Energeticum, which is located in Pickafeld in Austria. The available data for modeling, for a good modeling till now, is about 1 year, with a resolution of 15 minutes. The time series, the sampling frequency of the time series is 15 minutes. And before modeling, we have implemented a data pre-processing procedure where we clean the data, removed the missing values or values that are not reasonable, and then also we excluded some outliers of the data, etc. Also, we resampled the data to hourly resolution because our goal is to make a forecast 24-hour ahead, for example, for the weather data or for the energy consumption and PV power generation. So here you can see a histogram of electricity with the 15 minutes resolution, where you can see the peak here around mean is 2 kilowatt hours, which is the most frequent value. And also the mean daily value, which is not depicted here, is about the total value, I mean, is about 70 plus minus 20 kilowatt hours. Also here you can see for each month of the year the pattern that the electricity follows, where you can see during the day we have some peaks with and in the weekends you have less electricity consumption, maybe due to the fact that the building is closed. Also here about the peak electricity load per day of the week, you can see that for all days there is no specific pattern during the day, so this may be a difficulty for us to make some predictions in the future. Also, you can see here per month, which we can conclude the same. meaning that the month is not playing a very crucial role in the forecasting of the electricity consumption, because during the year the building is used equally. So here, for the data about the production of electricity, we have an example of 3 months here of the production of electricity from photovoltaics and the global radiation. The key here is that the variable that drives and helps to forecast the production of electricity in 24-hour horizon is the global radiation, which is very obvious here because this is the variable that produces the electricity. Also here you see some box plots about the explanatory data analysis of temperature variable and short wave radiation for another demo site in the PRELUDE project called RAI, which is in Denmark. And you can see, for example, for the temperature versus the week, we have a peak around the summer, and during winter we have lower values. And about short wave radiation versus the hour, you can see that during the sun hours you have more radiation. Also, this pattern follows this pattern. The PV generation is follows. Also here you can see the box plots for each hour about the electricity consumption for the Living Lab Energeticum building, where you can see that in the NAT hours the variance is not very high, but during the day it's very large. Also, this conclusion makes us understand that it's more difficult to make predictions because there's no quite separation and an hourly pattern like the PV production here. So it's more difficult for us to make accurate hourly predictions in the future. So that's all for the part of the explanatory data analysis. And here we present the two tasks that we have in PRELUDE project. The first one is forecasting weather, where we had data we acquired data for 5 demo sites. One of them is Athens, where you can see that we made the predictions for the temperature variable, for the global radiation, direct and diffuse. The model that we use is the LSTM, which is a deep learning model. Sorry. The training set that we used is about 25 years, and the test set to evaluate the performance of the model is about 5 years. And we can see here that based on these two metrics, the R2 and the mean absolute error, we achieved very good results. For example, for the temperature variable, we had an R2 about 95% and a mean absolute error of 1.4 degrees of Celsius for the temperature, which is a very good results for a test set of 5 years. So that's all for the part of the weather forecast. Also, I forgot here to say that for 2 consecutive days, we have the real values and the predicted values as I presented for the time series. So for the weather variables, for all weather variables and for all demo sites in the PRELUDE project, we achieved very good results because we had a lot of historical data to train our models. And as I said before, it's very crucial part of the accuracy, of course, of the model to have a large amount of historical data. So about the forecasting of energy consumption and energy power prediction, we used a tree method, a tree machine learning model to forecast 24 hours ahead the energy. Here we have few data about 1 year in order to capture, of course, in order to capture the whole operation of the building. Then we used a test set of 2 months from the 1 year to test our algorithm. Here the results, we have a more worse performance than in weather variables due to the fact that we have a few historical data. So the concept here is that electricity consumption has a white noise behavior, which means that we don't have a value of present time does not relate too much with the historical values. So it's more difficult to make accurate prediction. And in the case of the PV production, it's easier due to its nature because it has a behavior like global radiation. So you have the bell shape, and of course it's easier to have predictions in the future. And that's why you can see here in the metrics table that for the case of the PV, we achieved about 80% of R2 and about 65% for the case of the electricity performance. But here, this result may be misleading. The crucial part is the mean absolute error for both variables, where by average we achieved about 0.7 kilowatt hours mean absolute error, and in the case of electricity consumption about 0.4 kilowatt hours for a test set of 2 months. So that's all for our part in the forecasting models in the PRELUDE project. So some conclusions from this presentation is that the machine learning algorithms are the most contemporary way of time series forecasting. Also, there is a plethora of applications, as you maybe already know or you saw today, in the energy sector. One part of this is the forecasting of energy consumption and PV generation. Also, the manipulation and the processing of time series can be quite challenging because most of the times the nature of a time series can reveal the power of predictability, as you can see in the case of electricity consumption, which was a white noise, and this includes randomness in the time series. And finally, the main problem of time series and the main challenge to deal with is the forecasting horizon. So the longer the horizon, the more difficult it is to make some accurate predictions from for the MM models. So I think this is what you should keep. And that's all from my side. Thank you very much. And if there's any questions, I'm glad to answer to you. Thank you.
Thank you. Thank you very much, Nikos. Very interesting presentation. Now is the floor of Christian Heschi from FB. Hello, Christian.
Hello, I hope you can hear me well.
Yes.
Yeah, thank you also for invitation that I can hold here a short lecture regarding to the energy saving potential of data-driven predictive control. My name is Christian Heschi, and I'm Director of the study program Building Technology and Building Management at the University of Applied Sciences Burgenland. And I'm also in charge of the Center for Building Technology of our research substitute Forschung Burgenland. What we would like to learn in this lecture today, in the first step, I would like to talk about the need of a data-driven predictive control, especially regarding to the decarbonization of our energy systems. Here, data-driven predictive controls plays a really key role. And for this, I would like to analyze this topic more in detail. Then, if we talk about predictive control, model predictive control, data-driven predictive control, we have here two approaches to consider. The one is the development of a state space model. So for these reasons, we have also to make us more aware what is a state space model and why we need a state space model. And then we have also to talk about optimization algorithm. And here we will also analyze the possibilities of different optimization approaches. And then we will also discuss why we should use linear state space models and why we should use linear optimization algorithm. In the next step, we will also show how we can implement a data-driven predictive control. Of course, we need data. So for these reasons, we have also to prepare our building energy management systems in such way that data can be offered, not only current data, actual data, we need also historical data, especially for the parameterization of the state space model, etc. And for these reasons, we have also to analyze how we can implement and then which infrastructure we need if we would like to apply a high-end data-driven predictive control system solution in a building. And then, of course, we will analyze two topics. The one is the energy saving potential of such solution. And also I would like to discuss which additional energy or power shifting and power saving potential can be offer such solution. But now we would like to start with the data-driven predictive control possibility regarding to the decarbonization of our energy system. You know, if we talk about our energy strategy in the European Union, we have here a cascadized utilization of activities. In the first step, energy saving, of course. In the second step, the direct use of electricity, especially from PV and wind energy. So what we have here is in the future more volatile energy supply system based on PV plants and based on wind power plants. And for these reasons, we need a more intelligent control strategy on the demand side. So that means we may have to offer more demand side flexibility from the user side. And we have also to offer flexibility so that we have a more grid-friendly operation, so that the grid will be also have a better solution for the future. And for these reasons, we have here to develop as intelligent sector coupling technology. That means on the one side, we should use more electricity, especially for e-mobility, and then, of course, for power to heat and power to cool solution. The main advantage is that all this technology available at the moment. So we have not to wait so that, for example, batteries available, heat pumps available, etc. We have the solutions. We have also the solutions for communication. We have also the solutions for sensors, etc. We have only to put together all in an intelligent way so that we can align the energy production to the demand side. And this is in which case especially data predictive contour can help us. And of course we know that there is another topic in the future. It's the power to X and X to power technologies, but here we have still issues. On the one side, we have developed low temperature electrolysis systems, but we know also from the thermodynamical point of view that high temperature electrolysis has a more efficiency solution, or gives us a more efficient solution. For example, we can directly use the losses, the ohmic losses, for example, to transfer water to hydrogen, etc. And here we have still an open issue regarding to the development of the different cells and also for the catalytic materials. And here we have to wait. I think it's not possible that we can transfer this technology until 2030. And for these reasons, more and more plays sector couplings technologies a role for us for the decarbonization process of the energy system solutions, and also especially the intelligent building energy management system. What are the main advantage of a DPC, a data predictive contour algorithm? With a data predictive contour algorithm, we have the possibility to make peak shaving, load shifting. That means we can, for example, also ensure a power limit. We have also the possibility to optimize the runtime or the turn off time. This is really important, especially if you would like to apply heat pump technologies for power to heat and power to cool solution. For example, if you switch on and off the heat pump in a period of about 2, 10 or 5 minutes, then you have a lot of disadvantages. On the one side, you reduce massively the efficiency of the heat pump solution, and of the other side, you produce operating condition which needs a high maintenance cost, and for these reasons, a DPC controller can offer a wide range of different advantages compared to a classical two-point controller or PIT controller. We have also the possibility that we can better exploit solar gains. For example, if we not only use the DPC controller for heat pump or for the charging controlling of the batteries, if we use the DPC controller also for an active shading system, then we can use the solar gains directly for heating, so that we can avoid additional heating energy demand during the transition period between the winter and summer. This is also a really, really important topic. And what we can also do, we can do a more correct planning or correct sizing of the energy supply plants. What I mean is here, for example, if we use a conventional sizing of a heat pump solution, then we have the main problem that the full load hour is really, really low. For example, only a few hours per year. And for these reasons, we have often operation conditions for more partial load situation. And here we have, of course, additional losses, and the efficiency can also increase in this situation if we apply DPC solutions. So that means DPC plays a really, really important part for our future energy systems. And the question is, how does it work and how we can construct a DPC solution? And here it is really important that to understand what is a state space modeling, and of the other side, how we can optimize the future trajectories of the different actuators which we can contour. For example, the switch on-off situation of a heat pump or the change of the hydraulic valves, etc. And for these reasons, I would like to start with a first step. What is a data-driven state space model? We need a model which is able to predict, for example, if we apply the DBC controller for a zone, which is able to predict the room temperature. We know if we have here a building, then the room temperature depends on the energy which we feed in via heating, for example, in a zone, in a room, but also the temperature in a room is dependent on the inner loads. For example, if we have a lot of PCs, then of course the inner load also increase the temperature level in the rooms. Then we have also inner loads by the occupants. Everyone gives up if the occupants are sitting about 80 watt. So we have here also an increasing of the temperature based on these inner loads by occupants. Then we have also solar radiation, solar gains, which also, especially over the summer months, heat up the rooms. And for these reasons, we have not only to analyze in a state space model, of course, the energy which we feed in by heating, or which we extract by cooling over the summer season, we have also to consider all different loads which can occur, especially the solar loads if we use large glass fronts in our building. And especially if we have a lot of people in a building, then we have also to include the production, the heat production by the occupants. This is the one side. The other side, if we would like to align the energy consumption of a building to the energy production, to the energy yields by PV and wind, then on the one side we need a weather forecast so that we can predict the yields. And of the other sides we have to align, to reduce or to modify, to adapt the energy consumption of the building to the production. And this means we have here an impact from the energy consumption to the room temperature. This can be shown in the following slides. You can see here that based on different energy which we feed in during the heating case, the room temperature will change. Of course, it's not only the heating case, as I mentioned before, which we have to consider. We need also additional information, for example, the solar insolation. That means we need, in a first step, a model which is able to predict the room temperature independence of all these additional boundary conditions, and with consideration of the future development of the weather condition, of course, also with the future development of the occupants, of the occupancy. So we need also occupancy modeling so that we know in the next 24 hours, for example, how many people are in the room, are in the building, etc. And what we have also to analyze is, on the one side, as I mentioned before, to modify, to adapt, to adjust the energy consumption in such a way that we can better integrate renewables, but also we have to consider the room temperature in such way that we can offer with the building optimal thermal comforts. So that means the state space model offers us connectivity between the energy which I feed in a building for a future, with a future trajectories, and of the other side we receive information how, based on this energy which we feed in the different zones, how will change the room temperature. So but there are a lot of different possibilities how we can derive such state space model. We can use, for example, a black box model. It's a full machine learning algorithm. We can also use a white box model. That means we use a building simulation system and the building simulation model, and based on the building physics information and the weather data, we can also simulate the behavior, the thermodynamical behavior of a building. But there are also a possibility between both methods between both approaches, and this approach is called gray box model. The gray box model is a mixture between a physical model and a data-driven approach, and this gray box model consists generally based on the first law of thermodynamics. So that means we can use the first law of thermodynamics, and based on the first law of thermodynamics, we can derive, based on different model structure, a state space model. And in a first step, it is really important that to analyze what or which building we have. For example, if we have a building with a large glaze facade, then we have also to consider in the model structure the solar gains, the solar loads. If we have a building with a ventilation system, then we have also to include, of course, the energy feed in and extraction by the ventilation system. If we have a building with a lot of people in there, then we have also to consider the inner loads based on the occupants, etc. That means the model structure development develops, of course, from the application, from the building scenario, from the building needs. This is the first step. The second step is the model structure include thermal inertia, for example. There are also resistance, for example, for the U value from the exterior walls, etc. And this value can be directly identified based on measured values. So that means independence of the used building automation system and independent of additional used IoT sensor technology, measurement data are available, and the model structure should be also derived based on the available data. So sometimes if we have many data, perhaps we have only one room temperature and only the energy which we feed in the entire building, then we can only derive a model structure for the entire building. If we have more detailed information, for example, directly for each room, we have the energy supply, we have the room temperature, etc., then we can derive a state space model and a model structure for each room, for each zone, and then we can combine, put together it to the entire building. So, and this is also really important for the state space modeling, which information is given by the building automation. And based on this measurement information, we can parameter, identifies the parameter of the model structure, and then we can predict the room temperature independence of the boundary conditions, independence of solar loads, etc., etc. But really important is we should use here a model structure which is based on a linear BDE. The main advantage is, based on the linear BDE, we have the possibility that we discretize this BDE in such way that we receive a linear set of equations. And then we can derive, based on this linear set of equations, the constants, the matrix constants, in such way that we can better integrate it in the optimization algorithm. Of course, there are two possibilities. We can use the standard state space model discretization, but if we use a standard approach, then we receive nonlinear equations, for example, if we consider the solar loads, etc. And then we can only use nonlinear optimization algorithm. And if we would like to optimize a lot of different trajectories for the actuators, for the valves, for example, for the shading position, etc., then we have a big issue, because nonlinear optimization algorithm have here problems to find the global minimum. For these reasons, we use here source terms, which include in a in an explicit manner the nonlinear terms, for example, the solar loads, etc. And then you can derive here a set of linear equations. And this is a really, really good basic for the optimization algorithm and to apply, for example, a solver-based optimization. So if we have this state space model, then we can put it together with the mentioned optimization algorithm in such way that we can construct a DBC controller. In a first step, as I mentioned before, it is really important to analyze the building in which we would like to integrate a DBC controller in such way that we analyze what we would like to control. Is it only the heat pump switch on and off, or is it the heat pump? Is it also the different zones? Is it also the shading system, the position of the shading? Also, for example, the angle of the slats, etc. This is a first step. Then we have to analyze, are the data, the position of the shading, for example, also the condition of the heat pump, etc., are available in the building automation system, or should we also include additional sensors, for example, IoT sensors? Then we can derive, based on this information, the state space model, which include, if we have a large glaze facade, also the solar load behaviors, etc. And if you have, for example, a concrete core activation, a thermal activated system solution, then we have also to include additional capacities, etc. Dependence on the situation, we have derived this model structure, and then we can use the historical data to identify the parameters so that we receive the resistance, the thermal resistance, the thermal capacities of the different elements in the model structure. And then we can derive, based on this matrix form which I have shown before, directly the needed coefficients, which we can integrate it direct in a mixed integer linear programming optimization. This is a really, really important step, but this must only be developed one time. It must not develop for each building, because this principle model structure can be really general developed, which include all possibilities, for example, shading system, for example, heating system, floor heating system, etc. And then the model structure is fixed. The different features will only be switched on and off, independence of the building and the technical levels of the building. And then automatically also the metrics for the mixed integer linear programming will be derived. So this is the main advantage. So we have here one process which can be automated so that it's more scalable for different buildings. And then based on the predicted data, which we have so in the last presentation from Core, here, for example, we receive predicted data, weather forecast data, BV yields data, etc., and also the boundary conditions which are needed. For example, based on machine learning algorithm, it is possible to predict the behavior of the occupants. That means how many ventilation or air exchange rates we need in the next 24 hours, etc. This can be also predicted, and this will be also feed in as a boundary condition, of course, for the optimizer. And then we have also to consider the thermal comfort constraints and also the objective function. So we can use here, for example, comfort constraints regarding to the lower temperature level to the upper temperature level. The temperature band can be directly derived by user feedback or can directly given from the building manager. Regarding to the objective function, we can use here different objectives. We can optimize the self-consumption if we have PV panels implement it. We can optimize grid flexibility. We can optimize, for example, the operation for the heat pump so that we minimize the maintenance costs. We can optimize, for example, also the energy price. So if we have here time dependence energy prices, we can this also use for the optimization function. We can also use, for example, carbon dioxide as optimization goal so that we minimize carbon dioxide footprint. So this is really simple to change, independence of the general goal of the building, of the operator. We can use here different objective functions. And then, based on the optimization, we receive the contour inputs for the next 24 hours. And based on these contour inputs, we control for the next 24 hours the heat pump, the valves for the hydraulic system, the positioning of the shading system, etc. And the main advantage of this approach, if we use a linear state space model and if we use mixed integer linear programming in combination, the main advantage is we have here a really quick optimization algorithm which uses really low computational or which has really low computational efforts. That means the energy which we use for CPUs is really low. For example, if we talk about a really large building with a lot of zones and with many contour activities, shading system, valves for each zone, heat pump solution or storage, etc. We are lower. We are in the area of about several or 0.2 seconds, really quick. And if we have only one building with one zone, we have a low-tech building with a simply HVAC system, then it's really quick. It's in the area of 0.000 1 second. So it's really quick and really fast, so that we have here not a problem that we need a lot of CPU computation. Of course, the parameter identification, it's a nonlinear solution, costs a little bit more, but the parameter identification must only be done every 24 hours or every few days. Okay, we have applied this solution in our Living Lab Energeticum as a pre-pilot in the PRELUDE project, so that we can learn here how we can implement such solution in a building, then how we can optimize such solution, and also how we can derive this high-tech solution to low-tech buildings. This is really important also for the PRELUDE project, so that we can consider all bands which we have in the practical use. Here you can see that the picture of our Living Lab environment. It's a real building, it's real used. We have here also, of course, a feedback of the user. We have here a really critical building. This is the criticalst way which you can have. We have here a glaze facade, a full glaze facade. We have a shading system. We have here a concrete core activation. We have also floor heating system. That means we have here not a radiator, a classical. We have here systems which have a high thermal inertia. So on the one side, we have a really quick disturbance, change of the disturbance of the solar loads, for example, and of the other side, we have a really a low speed heating supply system with high thermal inertia. And this is the most critical situation which you can have. And if the system solution works for this critical solution, then of course you can use it for other really more simpler buildings. How we can implement such DPC solution? As mentioned before, we need historical data so that we can parameterize our state space model, and then we need also weather prediction, forecast data, so that we can apply our optimization algorithm. We derived here a concept which is also scalable based on an open communication platform. That means we use a building automation communication network. The backnet system is open. And what we did is we derived which sensor information we need, and then we used gateways so that we received this sensor information, for example, for the heat pump, for the rooms, etc., for the shading system. And based on the gateways, it is able to offer all the data in our backnet. And then we have installed a so-called H device, and based on this H device, we can offer all data which our partners needed. For example, the weather, the weather data from our weather station will be used by core to develop the weather forecast machine, the weather forecast module. Or, for example, we can also use the data from the occupants and carbon dioxide values, etc., to develop an occupancy model which is able to predict how many people will be in the building in the next 24 hours. And this also, for example, the classical energy supply systems, energy systems for the devices, electrical devices, etc. And we have also implemented the DPC controller directly in the backnet level. This gives us a little bit more advantages because we are not dependent on the internet connectivity. And here we used an OPC server. This gives us the opportunity to directly have here a bidirectional communication between the DPC algorithm and the actuators and the different sensors which are installed in our building system. That means we can collect the data, we can analyze the data, we have also the communication between the TPC and the weather forecast module, etc. And of the other side, we have also the possibility to compute the optimized trajectories for the actors and then to set the values or to change the set values and write these set values in our building automation communication network so that the controller direct control the heat pump, the pumps, etc. Here you can see, for example, a short comparison between measured and predicted room temperature based on a gray box DBC model. Which include also the forecasts, for example, occupancy forecasts, etc. What you can see, of course, we have not a 100% accuracy, but within the given temperature band between 21 degrees up to 25, 26 degrees, we receive here really, really good results. That means with a really simple linear gray box state-based model, which is data-driven, developed, we can really good forecast and really good determine the behavior of the room temperature, independence of the solar loads, independence of the inner loads, independence of the occupants, etc., etc. And we have, of course, this also implemented in our living lab in such way that we can analyze here the energy saving potentials. And here only some extractions of our intermediate results here, for example, for the cooling energy, so that you can see and get a better feeling how many energy we can save, especially for a cooling case. Of course, we have with our living lab Energeticum a building which is glass front, so that means that the solar gains and the solar loads for cooling case plays a really important role. And of course, we have also a full ventilation system with a cooling coil for dehumidification. And if we optimize all these aspects with DPC algorithm, That means, for example, if we know that the sun is really shining in the next 24 hours, then we control the shading system in such way that we avoid overheating in the room, so that we really need only low energy amounts for cooling, etc. Then we can dramatically reduce the energy consumption. Here you can see the intermediate results for the entire cooling energy of the building from May to end of December, for example. The red line are the energy consumption with applying of this DPC controller, and the blue line are the baseline. This is a standard controller which we have used 2018. Here you can see here we, especially for cooling case, for this situation with this glass facade, we have a huge amount of energy saving potential compared to conventional control algorithm. Also, we can see that we have here for heating case reached really a good reduction of the energy consumption. Of course, not so much, because we cannot change with an intelligent control algorithm the U value, the thermal isolation behavior of the building envelope. This is not possible. But what we can avoid is a too much energy consumption, especially in the transition period between winter and summer. Here we have the possibility that we can use for cooler transition periods the solar gains based on the intelligent contour of the shading, and of the other side we can also avoid additional energies, heating energies, which we need for the dehumidification, because here we use also after heater. And if we don't need the after heater, because the DPC can also predict the energy, the temperature increasing during the distribution pipes, etc., then we can also avoid this energy. And for these reasons, we can here also expect the long-term test. The one-year test is not finished, but what we can see here, we can expect that we have here also a really huge amount of energy saving potential for heating. And another really important advantage is that we can use here, or we can optimize here also the integration of PV. So that means self-consumption is also optimized here. So now I'm on the end of the presentation. What are the next steps regarding to the DPC controller? Of course, we would like to finish the long-term test, or we will finish the long-term test. So I think with end of May, we have finished the long-term test with the high-end DPC controller. Then we can also give you the information about the entire energy saving potential of the entire year. We would like also to analyze how we can apply it, and what are the potentials of such solution for other objectives, especially for energy costs optimization, carbon dioxide minimization. Then we will do also some tests regarding to the load shift, peak reduction. Here we have also interim results, so that we can, for example, say for cooling case, we have reduced the peak loads from about 30 kilowatts to 5-6 kilowatts. It's also a huge amount. Then it was also able to replacing the gas boiler. So 2018 we used the gas boiler for heating, because the ground heat exchanger was too small sized. But with this DPC controller, we can use the ground heat exchanger and can apply the heat pump solution for heating, and we don't need the gas boiler at the moment. So here we have also optimized the usage of renewable energy, and replaced the fossil fuel gas boiler system solution. Okay, PV self-consumption optimization I have mentioned before, and what we also will be analyze in the next few months is also the avoiding of maintenance intensive operation conditions, especially for the heat pumps, so that we can also show that we can save here costs, because the maintenance cost can be reduced if we have the optimal runtime for the heat pumps situation. And at the moment, we are working on the transferring of the DPC solution. Here, the main topic is to analyze the pilot situation, which technologies are implemented, and how we can derive, based on the pilot needs, the right state space model. And this is the really, really important part, especially for the PRELUDE project. And this is at the moment the most focused topic in our development of the DPC algorithm. So far from my side, thank you so much for having you. And I give forward the words to Giacomo.
Thank you very much, Christian. Very dense and interesting presentation. We will start, we will have two last presentation, the one from POLITO and the one from STAM. On this one from POLITO, we will shortly look inside some basic functionalities of the new platform for building white box modeling using Energy Plus. But mainly we will focus on one of the user scenario, which is the 24-hour forecasting. It's true that white box modeling is not potentially the best strategy not to support optimization, because as we will see in the limitation of what we will present today, requires a long time of running and elaboration and so on. But what we are testing here is in some way to push as much as possible these possibilities, identify and clarify better the limitation. In addition to that, it's clear also possible, as we will say, to pass, and we hope to do it in the next months, also part of this optimization from white box, fully white box to gray box or surrogate modeling. The presentation is done by me and by engineering Paolo Grasso from our group, and we will do it. Go, Paolo.
So let's talk about PREDICE. PREDICE is a Python library or a Python tool which is developed by Politecnico of Farina. And in its base form, it allows different things. For example, the parallel running of Energy Plus simulations, the editing of the building models, so the idea files, and the analysis and computing of key performance indicators on both simulated data or monitored data. PREDICE stands for Python Real-Time Energy Dynamics and Climate Evaluation, and you can see in the picture that is composed by mainly 3 different modules. So we have the IDF editor, which performs the editing functions. We have the runner module, which creates batches of simulations to run them in parallel. And the KPI calculator module, which performs analysis because it has all different metrics and indicators. We also included an EPW compiler, which is useful to elaborate weather data and create the weather file to be run with Energy Plus. So besides the main modules, we also have the PREDICE scenario scripts. So they are Python scripts that use the models to run different scenarios. Usually they take 3 to 4 files as input and produce a database of results. As input file, we always have the IDF model, which is the building model. We have a JSON file which describes the actions that are needed to run the simulation. So, for example, editing actions, or also the indicators and KPIs that you want to calculate. We have the weather file, which is in the EPW format, but with the EPW compiler, we can convert CSV format to EPW if needed. And also, some scripts require the monitoring data when we want to compare simulated data with the monitored ones. Okay, this is an example. Supposing we are doing a sensitivity analysis, the runner module creates a different combination of the actions with the parameters that we want to optimize. And okay, so PRELUDE supports different scenarios like sensitivity analysis, a support to model calibration, which is semi-manual, but it can speed up calibration of a model by a lot. We can compare simulated data with monitored data. So after running a simulation, if monitored data are provided, we can compute the KPIs also on monitored ones. And we can support 24-hour forecast, so a scenario that we will explain in a while. Potential things to be included are the climate change analysis and resilience, which will include the Copernicus Era 5 dataset, which we could include some optimization algorithms inside the scenarios like sensitivity analysis and 24-hour forecast to speed up the computation time, and also potentially a surrogate model to simulate in an alternate way and speed up computation time even more for some demanding scenarios. Now we will explain the 24-hour forecast, which is a scenario that exploit the forecast weather data to predict the best component behaviors of a building to maximize the thermal comfort. Components that can be optimized include the ventilation, which can be mechanical or natural, and also shading with its activation and slat angle. During the strategy selection, we will try to maximize the thermal comfort, but since we are using the adaptive comfort models, which is divided in zones, if some strategies are in the same zone, we try to minimize the internal airflow to have a better comfort, so minor ventilation issues inside the rooms, and also minimize the use of shading because daylight from the sun is preferred. This is the general workflow. So we have the IDF model, the building model, and the weather file as input files. The weather file is composed by the PW compiler, and it is made of historical data downloadable via internet or weather stations, and a part of forecast data which can be retrieved by online databases, for example, MeteoBlue. So we have this hybrid weather file, and if we feed our PRELUDE script with these files, the PRELUDE script will start creating the 24-hour forecast schedule. So based on division in blocks, we try different strategies for every block of hours. So for example, in the morning, we try combination of ventilation and shading. Then we try in the noon, and then in the afternoon. And during this analysis, we computed the thermal comfort with the adaptive comfort model for the entire day. And we select the best strategy that fits our model the best. So by repeating this for every part of the day, we finally assemble a final schedule which should be the optimal one. Now I can leave the floor to Giacomo again.
Okay, thank you, Paolo. So if this is the basic of the structure of the simulation platform that we are using, we have done a short 24-hour forecast test to identify one of the demo case building of PRELUDE project, which is set in Turin. It's a typical multi-block residential apartment building in cities like Turin, like I mentioned. So we are 10-floor building, okay, with 30 flats, okay, roughly speaking, and some of them is the one that we monitor and use and try to optimize for the PRELUDE project. In particular, we select one of them, and on this dynamic energy model, we run a 7 days test to verify how the 24-hour forecasting scenario for shading and ventilation in the cooling period. Okay, so reporting the cooling period for thermal comfort is going in respect to different control strategies based on threshold or based on basic control rules. Shading activation is independently given and oriented according to the orientation. The flat is oriented south and north, so clearly north and south has totally different approach in terms of solar gains. And the natural ventilation is again managed independently by each, we can say, window. One window in reality corresponds about to one thermal zone inside the model that we have for the flat. The interesting thing is that the optimized result for the 24-hour forecast model are compared with reference. I want only to remind that this type of building in which we are working is without equators. So all the things that we will do is a way to suggest to people, thanks to alerts after, action that they can perform. So also when we compare, we can say the different scenario today, some of these scenarios are not for sure, even the best one that we had identified without the 24-hour forecast, so the one based on fixed shading and strategies that work for this period is not potentially the things that people do. It's better and potentially is even easier that they follow a suggestion like the 24-hour forecasting suggestion that is not based on the fact that each day they remind at 11 to open. So that's the result of a different scenario. We have identified 4 scenarios. In particular, the first one is the scenario A, so base reference with no ventilation, no shading. Like people live here, it's a free-running building, they do not do anything, okay? There could be some random ventilation because they open, there could be some random shading, but mainly they don't control the building in itself. The test was performed in this week from the end of July, beginning of August, on Turin climate. And what we see, that's this distribution of adaptive thermal comfort model because we are in free-running, okay? What you see is the distance in each hour of this 7 days from the central line on the adaptive thermal comfort. Okay, so perfect comfort in the line, and the colors. So the green one is category 1 of comfort, perfect. The semi-green is category comfort 2. After we start to be in a sort of discomfort for category 3 and totally discomfort above category 3. What we see here is clearly that in this house is hot. Okay. If we see a second strategy we tested with basic analysis, that's again a reference case, there is no ventilation, but the shading is fixed scheduling during daytime. Okay, so they turn on at 9 and they turn off at 18, something like that, all the day. Like if you have a control rules with a timeline that open and that close the blinds. Okay, and we see that's slightly better, but not completely better. Okay. That's in summer, it's out oriented, so that should be. That is the third comparison scenario in which we have ventilation during the occupancy period. So like if you are in, you feel hot, you open, doesn't matter which is the temperature outside. It's quite typical, can be monitored in several cases in which people during summer open also during daytime, even if the temperature is higher, okay? And the shading activation arrives when the external ambient temperature is above 24 degrees, so like a typical potential suggested. Clearly, again, if you do not have an actuator, the fact that you shade after 24 degrees is complex to say that potentially people do. But we are trying to have good reference comparison. And as you see, totally is improved in terms of the condition inside the spaces. After that, we have identified an optimized solution by us. Now, architects, like building engineering, we say, okay, for this type of condition, for this scenario, we do some tests in energy plus interface till we arrive to a fantastic condition for that period, okay? And that's the best reference scenario. If our 24-hour forecast will replicate it, because we don't know what it will do now, we will optimize the shading and the ventilation profiling automatically without having a specific rule for choosing things. The rule is minimizing the discomfort in the 24 hours. So what this hour is doing is also look at on the impact that this hour will have on the next hour, since we are working in a thermal mass environment, so we have also the release of the mass. So that is working very well. The ventilation is activating during evening and early morning, so when the ambient temperature is sufficient to ventilate, cooling the space, and the shading activation is when the temperature is higher than 24. And that's even better. That's is the result of our optimized scenario, the 24-hour forecasting done with our tool. What we will see is that it's slightly better even, that the best scenario that we identify manually with specific threshold, the worst were for this week. So potentially this type of threshold, when we expand to the whole season, is not the best. While the 24-hour scenario is working perfectly, better than this. We are happy with this result. What is shown that the ventilation schedule and the shading schedule is given by the optimization in itself. What we also can see here is the fact that what we see is not only that we stay in the comfort lines, that is considered this line 2 for this requirement, otherwise we can also be more strict, but it's also evident we almost say always in comfort line 1, boundary after boundary condition, but also what we see is that it has reduced the difference in temperature, the variation in temperature with the day. That is a bit by the fact that we ask it to minimize the shading activation, to minimize the ventilation activation, considering the fact that people does not like to have shading on. We are in a residential building, okay? We do not have dimmer for lighting, okay? And this type of thing, so the less than possible in terms of modification. In reality, if we have under thermal stress, may also be not bad to be in a sort of stable temperature. That's clearly evident. And that's give the idea of what I just said. In all the cases, the 24-hour forecasted scenario is performing sensibly better. And if you look at the distribution of this comfort hour in the thermal category, it's the only one that completely cut off hour in category 3. So when we are not in comfort, okay, for the set that we say, and it's the one with the maximum number of category 1. Clearly, if you expect to extend to the whole period, it takes time to run the simulation. The whole period, this type of optimization, the 24-hour forecast has the potential to be better, even better than the others, because clearly the B3 is optimized manually to work as much as possible for this specific period. If extended, it will not be like that. If you plot it on the typical adaptive thermal comfort plot, we need to see that the 24-hour forecast scenario bring the discomfort to comfort. So for conclude, what we can say that clearly 24-hour forecasting model looks to work, which are the limitations. Calculation time, we use a server, a medium dimension server to run the simulation, because clearly to optimize it are run at, I don't know, 10,000, a lot of simulation, okay? In white box model using Energy Plus, so are simulated that takes some time to run. And the students present know, they work for that. A number of forecasted weather variables are required to feed this type of white box model. So we don't only need irradiation and temperature, we need more. And so we need to have, for example, external services for that, like Meteobur and things. But potentially, and we already have done the total connection to them, but clearly that's require extra data. In addition to that, in self-actuation, we may have the fact that the results that we have with the simulation may not perform perfectly in the condition, because we will have the performance gap due to manual actuator. Next step planned is the implementation of it in the Turing demo cases with a better implementation in over the flat to test the performance and sending the alerts to the people. To finalize the long-term test in the FB Living Lab, because we already start testing it and it looks working, but clearly we need to do now a test in the summer conditions. And also we need to do the same that we are doing for Turing in the RU Arbor demo cases. We will potentially compare the result with other strategies, including the Neo correlation model in PRELUDE, at least under simulation, and we will end also with a typical control strategy like done today, optimizer for the building in itself. We are working now to speed up the simulation time, including NSGAS3 for optimizing the choices of the better solution, and not running a lot of simulation, reducing as much as possible the number of needed simulation to optimize the elements. And that's potential. I don't think we will do here for the model. We will translate the white box model into surrogate modeling with one surrogate production automatically each 24 hours. Thank you very much. Okay, presentation is visible. Audio we have. That's fantastic things to know.
Yes.
Leave the floor to Mattia Repossi and Lorenzo Farina. Okay. Please.
Let's go. All right, first of all, good morning, everybody. It's a pleasure to be here. And a lot of presentations today, a lot of information to take in. And we hope today, even being the last one, so we try to give a little bit of a different perspective on the project. So we have talked a lot, we've heard a lot about models, about data, everything that we're doing in this project. And at this point, we would like to move the focus a little bit to what are the services and the product that we'll try to implement, and what impact they can have on our the society, on our customers, on the citizens and decision makers, and so on and so forth. So what we envision as STAM is that in the end, we're going to need to provide some kind of software solutions for each and every one of the stakeholders that kind of are around this project. And I can. Okay. So to do this, okay. So to do this, I figured it'd be interesting to give you a very, very short presentation of what STAM is and what it does, and how we involved in this project. So STAM is SME, an Italian SME based in Genoa, just a 2-hour drive from here. 50 people, 4 offices, 5 million turnover, more or less. I don't know why the slides went on. And just a few numbers to see what we are and what's our dimension. So what is our main expertise? We have a division that works with, I don't know what's happening. Robotics and mechatronics, modeling, simulation, research, innovation services, and digital solutions. And this is where me and Lorenzo are currently working in. So as you can see, a few things that may sound familiar also in the PRELUDE project, especially when we talk about modeling, simulation, research, innovation, and digital solutions as well. Go a little bit more into depth. We work a lot with DSS, so decision support tools. We work with advanced sensing, obviously modeling simulation, which I already mentioned. Automation and robotics, which helps us in the actuation of things. Digital solution, which helps us to put everything together. And then AI to model, analyze, and journal work with big amounts of data. If we can move on. So all this brings us to the EnPower platform. The EnPower platform, it's a one-touch stop for all the services that we're developing in the energy domain. Among these services, there are a few services, a few things that we have already developed that are available, and other they were working on, and especially one of them, we are working on within the PRELUDE project. And so we are trying to inject value from innovation into some solutions that then they can then be deployed either on the market, to partners, and to anybody who is really interested. And so the EnPower solution has 3 main pillars at the moment. 2 of them, well, the first one it doesn't really have much to do with the PRELUDE project, so I'll just be extremely fast. It's the bill checking system. It's just a way to match between your actual energy consumption from IoT and your energy bills, which is very useful because often energy bills, and I'm not sure if there's anybody from Iran here, but are very, very confusing. It's really hard to figure out what you're paying and how you're paying and when you're paying it. So this is just a way to put the 2 things together. We are working on it. At the moment, it's based just on data input, but we are trying to extend it so that it uses OCR to read from actual PDF documents and from invoices, so we can get the data and then work with that. Then we have the energy efficiency model and the behavioral demand response model service. Sorry. Everything, however, starts with a dashboard, because when we talk about data, we talk about models, we need to find a way to present this to users that do not have any idea of what we're talking about, pretty much. So this is what the dashboard looks like at the moment. So we have a few graphs that kind of give out the information on the costs, so how much we're spending on energy, how much we are consuming, what's the difference between the current month and the past month, and also what are the appliances that are withdrawing energy from the withdrawing energy, and what is the energy intensity, which is a good way to compare different households, different offices, because obviously it divides it by square feet, so it gives you just a unique KPI that allows you to compare the different things. And then the carbon footprint is just a way to convert the energy saved into CO2, and so see how much how well you're doing in this scenario. So this just, I'm going really fast because there are other things, but the main idea here, regardless of what kind of graphs you're showing, it's you need to translate the information, the data that you have that comes from IoT into a way that people can consume it in a way. So this is quite straightforward, but it's really, really helpful because in the end, you're not going to be able to deliver value if people do not understand what you're doing. So how do we do this? Again, really, really fast. To do this, we need obviously IoT data, but we also need to map what we call the digital twin. So we need to know what this data refers to in terms of physical assets. So we need to know how a building is made, how many rooms it has, what are the appliances that are contained, what are the sensors that measure a specific value for these appliances. For example, if you have a washing machine, you may have tons of sensors. You can measure energy, power, vibrations, anything that comes to your mind. So things get really, really complicated really, really fast. So you need to have a way to store all this information in such a way, and you need a way to put this together effortlessly. Because if you don't do this, then all the complexity just keeps on getting higher and higher as you ingest more and more data. So this, and what you can see here is just a way to list all your licenses. Then you can specify your usage cycle, so how you usually turn on and off these appliances. You can specify if they're flexible or not, because some appliances might be flexible, other might not. If we talk about demand response, there's only some appliances that we can potentially control. I mean, there's no way in turning off the TV when somebody's watching. There's no way of telling somebody to not use the oven because it's dinner time. So you may give some insights, but in the end, there's really so much you can do for certain things. For others, as heating, usually, you have a lot more flexibility. So, and this is something you need to work with the users. So a way to do this is to ask them what they're willing to sacrifice in terms of flexibility. Well, what they're willing to sacrifice to gain flexibility. So moving on here, yeah, this is just a way to list all your bills. So not really interesting for the PRELUDE project, but it's also a way to keep everything organized. And really, this is the source for the information for the bill checker that I described a few moments ago. So we're coming to the heart of the platform, and this is where the PRELUDE project really comes in, because one of the main components of the platform is the load optimization. So feeding in all the data that you've seen before, so all the loads, feeding in IoT data, so energy consumption, and not on that, temperature, environmental data, air quality data as well. We are able to provide with a forecasted optimization for the next 7 days. So we're able to tell the user how he should manage his loads in order to achieve some kind of results. And what are the results? We'll talk about this in a minute. But keeping our heads just for one more second on the graphic user interface, what we have here, it's just, first of all, we have information of how money you're saving, which is crucial because it's the biggest leverage pretty much you have with users. Not the biggest, but one of the biggest leverage you have. And we show how much power it's needed for the 7 days ahead. We show what appliances are on and off for the 7 days ahead. And then we show how much we can guarantee thermal comfort during the day, because it's not always the case that you need to be in a comfortable situation. So the idea here is to have, based on everything we know, this is how comfortable you'll be in the next 7 days in particular times. Because, for example, if we have data about occupancy, we don't need to maintain thermal comfort if nobody is in the room or nobody's in the apartment. So there are really a lot of things that do come into play, and a lot of data. Again, our efforts are to visualize them in the best way possible. So now we're going to deep dive a little bit into the algorithms that we're developing. A lot of things have already been said, so I hope that kind of this links everything together. I'll just go on for a little bit, and then I'll leave the word to Lorenzo, who will describe a little bit the technicalities. But the idea is this: so we have a bunch of inputs being either measured or forecasted. So we have the consumption forecast, we have the occupancy forecast, PV generation forecast, and environmental forecast, which is pretty much weather. We have a set of constraints. We have technical constraints. So, for example, the maximum power that we can get from the grid. We have economical constraints. So we have the different ranges and tariffs that vary maybe throughout the day. We have comfort constraints. So we know that we need to keep the temperature within a set range for a particular time, or we need to control the humidity, or we need to control air quality. And so everything it's thrown at the optimizer, which in the end gives us a optimized scheduling for the next 7 days. So how do we do this? To explain it all, it's going to take a lot more than 10 minutes. So we'll try to really give you an idea of the core of the algorithms that we're using and how we are approaching this problem. Before I do so, a little bit of context for the PRELUDE project. We are a work package leader for work package 4. So we are working with La Silla Core Libra in order to develop the proactive optimization function, and then we also task leader for task 5.4 for the data-driven control of predictability. So I hope you see that there is a path. You get data, you work with them, you optimize them, and then you can try to control things. And so thank you for your attention. Now I'll leave the floor to Lorenzo, who will try to go a little bit into depth and how we approach this from a data point of view.
Yes, thank you. So as Mattia mentioned before, the developments in PRELUDE projects rely on the thermal comfort. So this module can be then, when once developed, can be integrated with the energy loads optimization module. So in order to do that, we need a thermal building model that since we are dealing with data-driven approaches, we can rely either on gray box models or black box models. So you probably already know which are the definition, but in general, gray box models are the ones which needs some prior knowledge, so some physical domain knowledge and data acquisitions, while black box models just needs big data acquisition and no to very few physical domain expertises. Since the gray box model needs few data, we want to study and develop this kind of approach, and in order to apply it to several pilots for different levels of automation. And in order to do that, we used a simple single thermal zone approach, as you can see in the figure on the left. So we have external temperature, internal temperature of the building, TB, and the internal gains, internal power inputs like the PL from the heat pump. And from a lot of data, historical data, we can estimate the parameters, in particular the R parameters, the R parameter. In fact, as you can see from the equations, the first one is the normal temperature equation, so the state equation. Then from that equation, rearranging it, it's possible to have the explicit form of the R value. But since we are dealing with time series of historical data, we will have a lot of R values. So which kind of value we have to use? In order to do that, we plotted, as you can see, the R value distribution. And this is coming from the Energeticum historical data, so 4 years of value, 4 years of data. And we, having this kind of distribution, it's possible to determine a range, a very narrow range of possible R values, as you can see near 0.02 more or less. And in particular, what we used is the one with the highest frequency, so the 0.018 Kelvin over watts. And after that, it's possible to build the model and having such the connection between the temperature and the energy inputs in order to then optimize the energy inputs. Then the other part in the development for the PRELUDE projects is the data predictive control. So once we have the model, once we have the loads optimization, we have to have a way of actually improving, actually optimizing all the units, thermal and electrical components of the building. How to do that? First of all, we need IoT real-time data coupled with the above mentioned thermal model and feeding it to the EnPower platform that is able, as I said, perform an optimization of energy consumption while having a thermal comfort. The main part, let's say the main part of this predictive control is that it can be flexible depending on the level of automation of the building. In particular, it can be in two ways, in two levels, so low-tech solution or high-tech solution. For the low-tech solution, the main approach is having, say, no actuation for the building, so there has to be a connection with the user. So how to do this connection? Through an API system that from the platform can direct the data and suggestion to the user that can be from chat apps like Telegram, WhatsApp, or directly to messages. For the high-tech solution, instead, there is a direct actuation of the building units, but these need a pre-existing building energy management system. So with this, I conclude, and thank you for the attention. If you have any questions, these are our contact information or any doubt or curiosity.
Thank you. Fantastic. Thank you. Thank you very much. Now I think it's the time for question, if any has it.
Okay, thank you for all the presentation that were really interesting for, I think, all of us. And I would like to ask something more related to the implementation part. And so maybe the part related to the ask to the citizens to implement your technologies. So maybe the last one, the second last one. And which were the main difficulties that you found in asking for the people, okay, are you going to implement this technology because we would control your scheduling system, maybe your ventilation and all of this? And I think that the oldest person in Italy, for sure, maybe are not really interested in it. So I would like to ask which were your strategies into searching this, proposing this new technology. Thank you for all.
If I can add something, because as well as the task that you've seen on the presentation, we're also supporting with the Turing demo site. So there is even a step before that. You need to convince people to provide data. So it's really complicated because obviously you need to do that in a way so that it doesn't really impact their lifestyle in any way, because that's the data point of view needs to be absolutely transparent. They do not need to have any sort of impact, because if you do that, it's already a big barrier that you need to push through. So this is the first comment, and we had problems, people disconnecting things, people reconfiguring things because they wanted to have the data on their app while we were setting up a whole different pipeline to get data. So a lot of stuff going on. So this is a really a big challenge to start with. For the for everything that comes later, to me the better way to do this is you need to provide them with results. You need to show them this works and that this has a positive impact on their lifestyle. So if we can manage to show them that they have a little bit or a big reduction in their energy cost. And then if this doesn't come at stake of their comfort, then we have a very good path ahead of us. Because obviously it's easy to say, I'm going to cut your bills, but you're going to be freezing in the winter, or you're going to be extremely hot in the summer. That really doesn't work. So it's really a matter of engagement. It's really a matter of showing people the results and trying to do that even in the shortest time possible, because people get instructed really, really quickly if they don't have any input and engagement.
Thank you so much. I would like also to give you a short overview about our experience with our living lab environment. Here we had a really specific situation. After commissioning of the building, we had a really big issue regarding to the control system of the shading system. So if we started with the using of the building, the shading system ran up and down, up and down, up and down with the conventional control approach, and within, I think, from 2 or 3 days, we had switched off the system solution. And what the situation was, that the occupants was more aware about the control system and the problems with the control system, and they had also a problem regarding to the temperature levels within the building. So what I would like to say is we had an initial situation that the thermal comfort behavior and the thermal comfort conditions in the building was not the optimal solution. And afterwards we get in contact with the occupants and said we have a new solution. We would like to try it, and based on this new solution, it is possible to improve the thermal comfort behavior. And after integration of this system solution of the DPC control, it was really, really better. And for these reasons, the occupants were really open about the new technology. So I think a really, really important topic is if you can improve both the comfort conditions and the energy efficiency of the building, then I think it's not a problem to integrate additional sensors, etc. But one topic is still open. If you would like to integrate additional sensors, which you can see, for example, with LoRa system, etc., then you have sometimes also discussions. So the best way is you integrate it directly in the building automation system so that you cannot see the sensors. And then you have not the problems with additional discussions and the acceptance of the users is better.
Thank you, Kristin. Do you have other question?
Maybe I can also add on top of Christian. It is maybe Danish perspective, but what is our experience from Denmark is that in the past people were more concerned about actually comfort condition in their living spaces and less on energy efficiency. And this is because of the cost of energy was quite low until relatively recent times. Now this focus is shifting. So people are starting to speak actually about energy saving, compromising the comfort for lowering the energy use, simply because the prices of energy has dramatically increased. We can see people moving from static tariffs of electricity to dynamic tariffs of electricity. We can see they're changing and adapting the use of their behavior to these prices. And they become actually more curious and interested in that. So they start to speak during the lunch breaks, etc. if they have an app to track their energy use, etc. So before there was no interest in that. And another thing that I wanted to maybe mention is, well, we as energies and indoor climate specialists, we often say we optimize the condition. So we have some kind of a constraint, as Christian was saying, and we believe that we provide the optimum to the building by automation of, for example, shading devices. And then the comfort on the dashboard looks okay, but at the same time, actually the residential in the residential environment, people are exposed to this shading device that goes up and down, and maybe removing the view to the outside. And itself, the shading device moving up and down is irritating. We can see the cases where such solutions have been installed and have been deinstalled after a short time. And it is nothing to do with that they were not providing the thermal comfort to the spaces. It is something that is not measurable. It is just for the frequency of the device moving up and down and removing the view to the outside. And they can sacrifice their optimum comfort condition just not to be irritated by these two things. And well, we'll see where we will go with that in residential conditions. I think we just have to make a clear distinctions that different things can be accepted in office conditions or working condition, and different things can be accepted in residential buildings. But we are in the right moment to test this, because there is awareness for energy efficiency at the moment.
Yes, I totally agree with Mikkel on this point. The worst thing to working with residential, but also in some cases with office, because if people clearly start looking now, the shading device is moving too fast, like not so well controlled, at least not with multiple threshold balance controlled elements. The risk is that if there is they turn it off when possible, okay? Because clearly no one wants to have this or changes in the lighting, even if it's banner with the dimmer. That's not something feasible. So I agree that that's one of the issues that we need also to solve in the application of this type of control. Thank you. Do you have other intervention? No. So thank you very much in general to all participants, speakers, and everyone who has this 3 hour and something of time now to listen and stay with us. I really hope that you also follow the next events of the educational event series, but also the Prelude site and the upgraded that arrives by the Prelude project in general. I really like, at least personally, this type of communication that we have today. That's clearer, not only inside the consortium, but outside the consortium, to know what is some of the trends now in the proactive forecasting and smart building in general innovation points. So thank you really very much to all. And for everything, clearly, you have the Prelude connection and contacts, and don't hesitate to contact us. We will be all happy to answer and discuss, and why not improve what we're thinking. Thank you very much. And see you next.